My name is Christoph Bleicher, and I'm head of the division Structural Durability at the Fraunhofer Institute for Structural Durability and System Reliability, LBF, in Darmstadt in Germany. I would like to talk a little bit about an investigation that we conducted on the fatigue strength of repair welded nodular cast iron for heavy sections, so particularly for wind energy and large machine components. The situation behind this topic is easy. We have usually the problem that, especially when we talk about such large components for wind energy application or also heavy industry application, that sometimes material defects or discontinuities coming from the casting process might occur. And especially on the surface or in the surface areas where we might have larger stresses or higher strains, we want to get rid of those discontinuities, and the possibility that we can take into account is the welding of such structures, as you know it from steel castings, for instance. But in contrast to steel, for nodular cast iron, there's only insufficient knowledge about the availability of data for the fatigue strength of those welded materials, and especially when we talk about a thick-walled nodular cast iron, so meaning wall thicknesses above several 10 millimeters up to 500, 600 millimeters. So at the moment, there are strong reservations about the accepting of repair weldings for wind energy components, specifically by the certification bodies like DNV. So our task in the research project called Nodular Weld was to analyze the fatigue strength of welded ductile cast iron. Particularly, we investigated the ferritic GJS 418 LT, which is one of the most popular and mostly used wind energy materials, a ferritic material that we welded with the Custom-Mag 45640 Ti material. Additionally, we investigated also a ferritic material, a GJS 450-18, with a higher silicon content, so a slightly increased tensile strength and also fatigue strength. Here we used an Endotech DO 23 welding filler. In both situations, the welding filler is induced in the component, or in the, let me say, in the void by a cold welding process, because among a lot of different investigations that we conducted, the cold welding process showed at the end the best results compared to a hot or a warm welding process. So we compared different welding fillers and different welding materials for those two base materials. You see here on the bottom a cast block that we got provided from different foundries. We milled this cast block here with a certain void, or with a certain geometry that had to be filled by the welding process. And here on the right side, you see the cast block with the welding before the machinery of the specimens. Looking at the different specimens that we investigated, we had actual specimens on the one hand taken from the base material. So we see here on the left and right side, next to the welding filler material, we inspected also the welding filler, so specimens being taken in the direction of the length of the block, and also specimens close to the heat affected zone to see if there is an additional effect coming from the welding and the welding process itself. Additionally, we used integral specimens to comprise the base material, the welding filler, and additionally the heat affected zone, and to investigate the, let me say, the material gradient, the fatigue strength gradient, and the material gradient in those specimens. Additionally to those actual specimens, we used bending specimens. You see here as an example those bending geometry with the welding, so also removed from the cast block. And here on the right side, as an example, the bending specimen, as you see here, 0.5 meter long, and a crack propagating from through the welding filler in the base material. Here an example of the fracture surface and a detail of the crack. The bending specimen is for us a measure to, let me say, transfer the data that we have from actual specimens that we need, for instance, for data for numerical analysis, to transfer those data from the actual specimens to the bending situation, to bending specimens that we have here, superposing the different materials, so the welding filler, heat affected zone and base material, with an additional stress gradient, which is typical for the components. Usually, especially in hotspots, no component will come, or a hotspot will not come without a stress gradient. And so a bending specimen is a closer step towards the investigation of a component. In fact, we were not able to investigate a complete component, especially from statistical point of view. This would be much too cost efficient, inefficient, and so we had to stick with those bending specimens. You see here an example of a test equipment. On a servo-hydraulic test rig, we conducted fatigue tests on a strain base here on the integral fatigue specimen with an extensometer with a gauge length of 50 millimeters. We conducted those strain controlled fatigue tests under R equals -1 until the limit number of cycles of 10 to the power 7 cycles. We did this for the base material, the integral specimens, the welding filler, and the heat affected zone. And additionally, the stress-controlled fatigue tests we conducted for under alternating and tensile loading until 10 to the power 7 cycles for the base material, the integral geometry, and the bending specimens. Here on the lower left side, you see as an example an X-ray picture, an X-ray result from our investigations from the specimens. So before we did the fatigue testing, we decided to make an X-ray analysis of those components, of those specimens, because we knew or assumed that there might be local smaller voids in the welding filler material. And as you can see here, those dark dots, now and then smaller pores in the welding filler occurred. This was at the end not really a problem, because it showed us that we are, even since we did those investigations and the weldings in a laboratory surrounding, we did not try to make a perfect welding, because at the end on the construction side, somewhere offshore or wherever you might repair such a component, also in the foundries, you will not have a perfect surrounding and you will not have a perfect result at the end. So it was better for us to conduct the fatigue tests on specimens that were, let me say, welded in a more or less serial or to a serial production compared situation. Let's have a look at the results. We see here the results of the strain-controlled fatigue tests in form of the cyclic stress strain curves. On the left side, we have the 418 LT. You see, in comparison, the red line and the black line. Here we have more or less no influence of the stress strain behavior when looking at the heat affected zone and the base material. This was valid for both materials, also for the 450 material. So the heat affected zone is more or less from the stress strain situation not really influenced. What we see additionally is that the integral material state and also the welding filler showed for the 418 LT a much higher stress strain curve, a higher strength. Nevertheless, looking at the Young's modulus for the welding filler, due to the voids and small pores in the welding, we have a reduction in the Young's modulus down to 142 gigapascal. The base material, what we see here, the heat affected zone, or here, is around 160 to 170, something around this. Let me say in the mean 165 that we achieved here. The same applies for the 450 material. We have here a lower Young's modulus for the welding filler material. This is necessary for us as an information for the numerical analysis. So when we want to model those welded structures, those welded components locally, we have to assign different material data, material information to those areas in the numerical stress strain analysis. So then we have to apply and assign a lower local Young's modulus to those welding filler. And this was one of the achievements here from the investigations, to see how the different regions behave in the stress strain region, and also to see if there are larger differences. What we have on the 408 LT, we have more or less no change in the for the 450 material when combining base material, heat affected zone, and welding filler. And on the other hand, we see this difference, this change in the Young's modulus. The the strain controlled fatigue test also showed us the strain life curves. We see here for the 418 LT on the left side the different strain life curves. Again, we have here more or less no difference between the heat affected zone and the base material. We have much higher lifetimes in the low cycle, and also in a certain range in the medium cycle fatigue for the welding filler material. The worst situation showed the integral material specimen, where we have, especially when we talk about high elastoplastic strains, we have here a reduction in the lifetime. Approaching higher lifetimes, up to 10 to the power 6, 10 to the power 7, and so on, those different materials approach each other for the 400 material. So we see for a long run not really a large difference in lifetime. This is a bit different for the 450 material. We have a stronger difference in the low cycle fatigue regime for the heat affected zone and the base material, while we have comparable material behavior for the high cycle fatigue regime. When looking at the welding filler, the lifetime and, let me say, the allowable strains are here a bit higher compared to the other situations. For low cycle fatigue, the welding filler is more or less comparable to the base material. So a complete different behavior depending on the base material, depending also on the welding filler material. Those data again help us to assign the correct data to the numerical analyzer on the one hand, and assess also then the lifetime when talking about damage sim accumulation on the one hand, and a strain-based lifetime assessment. Here is a summary of the stress-controlled fatigue tests we see for all situations. So for the actual specimens that we investigated, and the bending specimens that we have for the 480 LT as well as for the 450 LT, to take into account a strong reduction in fatigue strength. So on a stress-based view, we have to face at least 33% for a tensile loading for the actual specimens when comparing the base material and the welded condition, so the integral welded specimens. The same applies for the bending situation. Here the losses are much higher, and the same is also given for the 450. In one difference, the 450 was not able to reach those reduction factors as we have it for the 400, but exceeded those levels. So at the end, you see here that when we talk about the actual fatigue specimens, that we reach in the welded condition, although we start from a higher level for the base material, so for the not welded condition, we have such a high loss that we end up at a level on a nominal stress amplitude that is by far lower than for the welded condition for the 400 material. So you see and let me say one result here from the investigations. We made a lot of pre-tests on different welding fillers, hot welded and cold welded situations. For this situation, the 450 made us some problems, and we ended up with the Endotecto 23, which with the what we assume best results. And still, we see from the welding process and the fatigue strength at the end, we are much lower in the resulting fatigue strength, both for alternating and tensile loading. and both for actual and bending specimens in comparison to the 418 LT, meaning that especially when we have to take into account weldings, we will not profit and benefit in any case from the higher fatigue strength from the base material that a 450 material has at the end. So and we have to face weldings, and we might have weldings in highly stressed areas in the component. A 418 LT with a custom MUG showed much better results here. For the actual specimens alternating loading, we are having at the end approximately a factor of 2 in the nominal stress amplitude at 10 to power 5 times 10 to power 6 cycles. One example from a fracture from an integral specimen, we see here the welded area, and we have a fracture in the base material. But we had also fractures here in the welding at a pore, as you can see here. And another example in the welding filler, not due to a larger pore, but nevertheless in the welding filler, we have here the fatigue failure and the final fracture in the welded area. I would like to thank the Federal Ministry of Economic Affairs and Climate Action for funding the project Nodular Weld, and also the project partners supporting our research project. And finally, at the end, I would like to thank you for your kind attention. If you have additional questions, get in contact, get in touch with me, and hope to see you soon at another conference. Thank you so much.